So last time we stopped where we introduced. Maybe I'd better move to the previous slide. Okay. So we introduced, first of all, we are in the context of radiative transfer. So we are reviewing all the main processes that are responsible for either emission of radiation by matter, by gas, and absorption. So we saw spontaneous emission, and we began considering instead absorption. So we derived introducing the concept of cross-section, which of course is already familiar to you in other contexts, but in this case as a special, is particularly important, particularly relevant, and in particular the link between what we called the absorption coefficient, alpha nu, which is nothing but the product of the number density n, so number of particles, number of atoms per unit volume times the cross-section sigma nu. Sigma nu depends, it does depend on the frequency, in general. You change the frequency of the photon that can be absorbed, so in principle also the ability of a given atom to absorb it changes as a consequence. So that's why. And I also introduced the so-called mass absorption coefficient, or just opacity, which is kappa nu, which is just, as we saw last time, is nothing but the cross-section per unit mass. So dimensionally is an area over mass. And one of you last time made a very important point. So you said, okay, this proof holds as long as we believe that different atoms do not cast shadows. So they are not too packed in a way. So what does this mean? Let's see exactly what kind of assumptions we implicitly made. So we now made them we now make them explicit. So there are two assumptions essentially. The cross section cannot be too large, otherwise what we assumed last time doesn't hold anymore. In particular, if you think the cross section must be small compared to the typical distance between the particles, between atoms. If not, of course, the probability of two atoms just lying on the partially shadowing each other, hiding each other, wouldn't be no more negligible. But we don't want that. So we demand that what's the typical? We have to compare two linear scales essentially. The size of a single atom. So given that the cross section is what is relevant in this, we want to scale just a linear scale. So we take the square root of cross section. So we have a typical length. And we want this to be much smaller than the typical distance between different atoms. So how can we know that? Well, if you know the number density is number of atoms over the volume, which is also one atom over the volume of one atom. So if you want the volume of one atom, it's just 1 over n, just like that. And so if you have the volume of one atom, just the cubic root, and so just n to n minus 1 is the volume, so n to minus 1/3 is just the typical distance between atoms. So we want this. We want the size of one single atom to be much smaller than the typical distance between them. And so if you just square both terms of this inequality, you see that this is equivalent to asking the cross-section is much smaller than n to the minus 2/3. If you work out the product of the absorption coefficient, alpha nu times d, well, you know that this is a number because alpha nu is 1 over length. You multiply by the distance between two atoms, which we called here d. And so, again, alpha nu, we found that it is just as I repeated at the beginning of this class, it's just n times sigma nu. And as I just said just 1 minute ago, the distance is just n to the minus 1/3. So you combine this, and you find that this number is exactly sigma nu n to 2/3. So if the previous condition is already fulfilled, this one, this automatically implies that this guy is, which is a number, we know that, is much smaller than 1. But what is the meaning of this quantity? Well, you know, alpha I is the decrease of I moving along a given per unit length. So if you imagine to move by a quantity which is just the distance between atoms, it means that the absorption, the fractional absorption is much smaller than 1, so it's negligible. So this is another way to put this, to express this condition. So this condition holds true as long as the absorption over a length which is comparable with the distance, with the mutual distance between atoms, is negligible. Makes sense. And the second assumption is that, of course, the distribution, the volume in the volume of different atoms is such that they are randomly distributed. So they are independently distributed. There is no correlation in the way they are distributed in the volume. Otherwise, of course, the randomness assumption that is crucial to derive what we derived would fail. I think I have to hide this. Okay. Here I made an important point. So far, we considered absorption. So whenever radiation just gets decreases just because of the capability of matter of absorbing, there is also a specular process, which is stimulated emission. What is that? Well, we will see when we will be speaking about Einstein coefficients, so presumably next class. But essentially, what is that? Absorption, you've got one photon, it interacts with the atom, and then you lose the photon. So from one photon to no photons at all. In this case, you double. You've got one photon, so for the way matter works, the interaction of a photon can stimulate, can enhance, can make the atom itself to emit a second photon. So you've got one photon at the beginning, you've got two photons at the end. And this, of course, is strongly related with the radiation field. The stronger the radiation field in which the atom is surrounded, the more photons the more incoming photons you have. So the more photons you gain due to stimulated emission. So stimulated emission works much in the same way as absorption, but in the opposite way. So it is proportional to the radiation field itself, but instead of absorbing photon, it adds further photons. So you can think of, and you can describe exactly with the same formalism, with the same lines, following the very same lines of reasoning, you can think of stimulated emission as it were a negative absorption. So by allowing the absorption coefficient to be both either positive or negative, so by contemplating both possibilities, it means that you are implicitly including both effects. When it is positive, that's exactly what we've been doing so far. So absorption. A negative absorption coefficient means stimulated emission. And this is different from spontaneous emission, because spontaneous emission, the rate of photons created within a given volume, per unit time, per unit blah, 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 is unrelated, doesn't depend on the radiation field, while stimulated emission does. So that's the profound difference, which makes stimulated emission more akin to absorption, because it works in the same way. The only difference, well, notable difference, of course, but the only difference is that instead of instead of absorbing photons, it creates photons. So essentially, so far we consider three possible processes. Essentially, we bought three at the price of two. We reviewed spontaneous emission, absorption, and now we see that this includes also, as a matter of fact, also stimulated emission. So three ways at an atomic level in which a given atom can either absorb or produce photons. Okay, there is also another process which I will be dealing with, I will be commenting on next, which is scattering. In the case of scattering, the atom doesn't absorb and doesn't emit either. It just can change the direction of the photon as well as its energy. So this is another process which I haven't, for the time being, we will neglect, okay? Let's just keep in mind this. So let's put together, let's work out the balance. So how I, the intensity, can change. And you see that putting both contributions together is that, so di over ds is just the sum of these two contributions. Minus alpha mu I nu is exactly what we obtained for the absorption, if you get back. And while J nu would be alpha nu ds I nu, if you want the differential quantities, and J nu ds is just di. So both terms, if you multiply again by ds, you've got minus alpha nu ds I nu, which is the gain, is di derived in the case of absorption, when just absorption was considered, and when just a spontaneous emission was considered, we got J nu ds. So just dividing by ds. So this is called radiative transfer equation. Very general, very important. This is worth learning by heart once you understood exactly, once you can explain what is what, which is what, and where it comes from. That's very important. So essentially, this is encodes all the mathematics, all the mathematical aspects that are required to address, to solve the problem of understanding how the radiation field, how intensity changes moving along a given region of space filled up with matter. Again, I remind you, this is just in the case of when scattering is neglected. We will see later on how it changes when also the scattering process is included, okay? But formally, this gives you already a lot of information. In particular, you see both the capability of absorbing matter, which is expressed by alpha nu, absorbing in a general sense, because as I just told you, when it is negative, it means that stimulated emission also is dominating in that case. And J nu, the capability of producing radiation. From a mathematical point of view, including so moving to a more general equation, so including the scatter, makes the problem from a mathematical point of view much more complicated, because the scattering, as I wrote here, it becomes, instead of a differential equation, it becomes an integral differential equation. Why? Because you have to include a term which depends on an integral. Why? Because the scattering means that you have to consider all the possible photons that are coming from other directions, from all the possible directions, and are scattered towards your direction, towards ds. So it means that if you want to consider all the possible contribution from all the direction, you have to integrate over solid angle. So in the same equation, you have a function which shows up as I here, which shows up as its derivative, but would show up also as a function which is integrated. So that would be much more complicated. So this is just a point worth making. We define a new quantity here, and I define using the differentials. So we call this quantity tau, and by definition, the elementary increment, so d tau nu, is alpha nu times ds. So whenever you move in space by a displacement we call ds, there's some matter, so there is some absorption coefficient in there, it's depending on frequency. So we will have an increment in the so-called optical depth, which is defined this way. Let's make a consideration, a dimensional consideration. Alpha nu is 1 over length. ds is the length. So first thing to note is that the optical depth is a number, is adimensional. Okay? 1 over length times length. And of course, if you think of a path in space that suppose you are following a ray of light, so you start from one point, so you call S0 the starting point of your path, to a generic S. So by integrating this, you can associate to a given path also a given optical depth, which is just the integral following this, following the definition. And just a few names. There are two regimes which are so important to understand, and we will see. We'll spend a lot of time just on focusing and understanding the two different regimes. The so-called optically thin, or just transparent, which correspond to a path whose optical depth is smaller than 1. So whenever you have a given path and you calculate the corresponding optical depth, and that is smaller than 1, you can call it transparent or optically thin. And we will see why these names are very sensible. They really make sense. In the opposite case, instead, when this quantity, the optical depth, is larger, particularly much larger than 1, so 10, for example, you call this optically thick or opaque. Okay, these numbers now just make little sense to you, but things is going to change soon. So just getting back to the radiative transfer equation I put at the top of the slide. If you just simply divide both sides by alpha nu, you see that the right-hand side of the equation is just minus I nu, and then this ratio, J nu over alpha nu. And if you look at the left-hand side, at the denominator, you have alpha nu ds, which is exactly our friend, d tau nu. So it means that this equation, transfer equation, can also be expressed instead of ds, so instead of s as the independent variable on which, in particular, the function we are interested in, the intensity or brightness, depends on, we can think of, instead of function of s, we can think of f as a function of tau. What does this mean? Okay, I here simply rewrote the radiative transfer equation in the new fashion, so using the optical depth instead of s. And if you pay attention, what we got here was, the second term here was J nu over alpha nu. This guy, I call it S nu, and S nu, which by definition is the ratio between the spontaneous emission coefficient and the absorption coefficient, is called source function. So S stands for source. Why source? Well, we will see. Well, first of all, notice that S is homogeneous with I. So whatever source the source function is from a dimensional point of view, is some kind of brightness, has the same dimensions as brightness, okay? Because they are just summed together. Easiest way to see. You also see that tau is a number, so di over d tau still from a dimensional point of view is I. So these three terms are just brightness, essentially, from a dimensional analysis. Source function, well, I can immediately tell you that the source function is something which characterizes the properties of matter, also depending on the physical state of matter. So it might depend on temperature, on ionization state, whatever, but it's something which describes the properties of matter. Why? Because it's the ratio between the capability of matter of emitting spontaneous emission over the capability of the same matter of absorbing. So it's something, when you know the source function, it means that you know something which describes the properties, the capabilities of matter. So moving from considering I as a function of S, so as a function of the point of the variable which describes where you are in space, so the path. We now moved to optical depth. So it's kind of, you can look at it as if we had kind of made a variable change. So the independent variable change. So instead of describing the path as a function of S, so the travel distance along the path, it's kind of, we made a variable change. So we defined a new quantity, which is tau. And we saw when you change the variable, you have to know the relation. Here you know the relation between the differentials, which is what you need in a differential equation. So now our function, I remind you, our goal is to constrain to know I. So instead of considering I as a function of S, is now as a function of tau. Tau is adimensional, but it's still equivalent way to express where you are, how the kind of path that you traveled at some point. Okay, so one can see it just in this very simple way. So now the radiative transfer equation, solving that equation means to find a way to possibly get clues on this. We use a mathematical trick, and we introduced a couple of new functions. In particular, you see this letter is just, by definition, is I nu exponential ti nu, and I called it, this is a kind of calligraphic I, okay? It's very, calligraphic comes from the Greek, which means beautiful writing, something like that. So let me I will just call it just cal I, calligraphic I, okay, beautiful I don't know. So this is just a function. I defined a new function. You will see why this is convenient choice. And analogously for the source function, I define the cal S as the source function itself, S times the exponential e to the tau nu. So you can invert. So if you consider this one, you can express I as a function of cal I, just multiplying or get this on the other side of the equation. Easy, okay? So this becomes e to the minus tau nu. And the very same way, so the source function can be expressed as a function of the cal S exponential of minus tau. You now replace both I and S. You put them into you replace them into the radiative transfer equation. So let's work it out. So So the first term, you have a derivative. So derivative of I is this guy. So rules that you know very well. So you derive this, you derive cal I, and you leave this unaffected. So you have the derivative here, and just copy exponentials to minus tau, and then you do the same by inverting the. So you take cal I, and you just left it. You just leave it as it is, and you derive exponential of minus tau. So you gain a factor of just a sign, -1. So minus this guy the same. Equal what? Well, derivative, no derivative, minus I, so minus this guy, minus cal I exponential minus tau, and then the source function is this guy here. So you just copy it here. So we just express the radiative transfer equation by using these newly introduced functions, just like that. Very. Why is this convenient? If you pay attention, you see, you recognize the same term in at both sides of the equation. In particular, this guy is exactly the same. So this and this cancels out. And in particular, you are left with this one and this one. So you can simplify, you can remove the exponential term, and you are left with a very, very simple, much easier, at least formally, equation. So d cal I over d tau nu is just cal S, just like that. So formally you can express, of course, to know exactly the mathematical solution, you have to know exactly, you have to know the dependence on tau. But at least formally, it can express just by inverting, of course, the derivative operation, which is the integral. So the formal solution is just that cal I as a function of tau is just cal I at the beginning of the path, so I called cal I 0, so the initial value at the beginning of the path, plus the integral between 0 and tau nu of the cal source function. Now let's get back to our original functions. We don't care about these newly introduced functions. These were just a means to get to the goal. So let's replace back our. So here the term here I is just this guy. So cal I is just I nu epsilon e to the minus tau here. On the right-hand term, here we have the initial value of cal I. The initial value of this guy, if you pay attention, is just I nu at the beginning. Exponential of 0 is just 1. So that's why you have this term here. So exponential, I explicitly wrote here exponential of 0, but you already know this is just 1. Plus what? The integral of here cal S is just S, and you gain also an extra factor of exponential tau. Here they are. Of course, this is prime because this is the integration variable. Okay, should be quite easy to follow this, I guess. Now let's try to interpret this result. And here I wrote that the initial intensity, so the generic intensity after a given tau nu is just the initial intensity, I nu 0, which is diminished because of absorption. So this exponential, this negative exponential tells you how much the initial intensity has been suppressed by absorption. Plus what? Not only do you have the absorption effect of matter, but also the production, thanks to spontaneous emission encoded in the source function. And this is a less straightforward term to interpret. So I just made an extra slide to let you understand. So I here wrote the very same equation, the very same result, and I used different colors to emphasize their different meaning. So you have the path of radiation, which we now described with independent variable tau, as I said, instead of s. So let's assume we start from here. So we wonder what's I at this point. So this guy, what is that? Well, this guy is the result of what we already have at the beginning, and I just wanted to express this with this red circle here. But this is suppressed, partially absorbed, so diminished. The initial intensity, I nu 0, is diminished along this path, and this is represented by this term. The exponential, the negative exponential e to the minus tau nu is because this guy traveling along this path, which is tau nu, is diminished by this amount. Okay. Let's look at the second term. The second term is an integral with tau nu prime, which is the variable, which is integrated between 0 and tau nu. So this guy is moving. And what we are summing up, well, it's the contribution of the source function. And this guy is moving as well, so it depends on tau nu prime. But you not only have to add the contribution of the source function. Once you have the contribution of the source function right here, for example, you also have to consider that much in the same way as this guy was suppressed along the path. Well, here the path that has to travel is just this one. So the path here is tau nu minus tau nu prime. So you have to suppress this contribution by the exponential of this guy, which is exactly this term here. So the contribution of this one is also partially suppressed by how much? By this guy here, which is the exponential of the length that has to be traveled by the radiation produced here, right here. And of course you have to integrate because this contribution just happens, takes place all over the point in between. So that's why the integral, okay? So I also highlighted with the same corresponding color also in the sentence below. Okay, so the kind of purple color means the effect of absorption of a generic source along the path, which has to be within the integral because this changes depending when you move, consider different points along the path. So you see, now it should be clear the meaning of the interpretation of this equation, and it should also make sense if you think of the meaning of absorption, the way absorption works, as well as the way the contribution. To better explore the meaning of this equation, let's consider, so this is again, this is the very same equation, but let's consider a special case. A case in which the source function is constant. It doesn't change along the path. So that integrals become trivial because s is constant. I just called s nu. And the integral of that guy, easy task to carry out. I let you, this is just a very simple exercise. It's just 1 minus negative exponential. So let's try to figure out, this can also be rewritten this way, as s nu plus, you collect the minus the negative exponential, you see you have this term. Well, why is this interesting? Let's consider the case of an optically thick medium. So optically thick means that tau nu is larger, much larger than 1, okay? So very thick, very opaque medium. In this case, traveling such an optically thick path, this second term here, whatever it is suppressed by the negative exponential. So this immediately tells us something very interesting. Along a given path whose optical depth is much larger than 1, the intensity tends to approach the source function itself. So this brings us close to understanding the meaning of the source function. So provided that you move along a path which is optically thick, That's the requirement, to have the second term suppressed. So when tau is much larger than 1, I tends approach the value of the source function itself. And in particular, if you remember, which I put here, the radiative transfer equation, you can immediately see two different cases. The first case, when you are at one point along the path, and you in that point, at that point, the intensity is greater than the source function. If you look at the radiative transfer equation, you see that the negative term takes over the positive one. So it means that the derivative is negative. So in the case that the intensity is greater than the source function, the intensity will decrease along the ray. And the opposite case, of course, when you're in one point, and at that point, the source function is greater than the intensity, well, here, of course, the positive term prevails over the negative one, so the derivative will be positive. So the intensity function will grow, will increase, up to what? Well, if your path is optically thick enough, because you might have a region of gas whose optical depth is not necessarily thick. So depending on, but if the region is such that the corresponding optical depth across the region is optically thick, it means that whatever the initial I, in the end you have something very close to the source function itself. So you start appreciating the meaning behind the source function. Yes, so this is just what I just said. So again, let's move on considering all this case. Again, so this is again the case of a constant source function, okay? Let's assume, just for simplicity, that at some point, at the starting point, the intensity is just zero. The point you start from has zero intensity. So you see that the function which describes, the formula which describes the intensity along the path, you get rid of the initial term here, in this case is zero. Here I just rewrote the definition of source function. I remind you that the source function, by definition, is just the ratio between emission and absorption. If you multiply both numerator and denominator by r, where r is the size of the typical region in which you are moving, so the size of the source, this allows us, and remembering that tau, let's consider again all these use cases because this is easier to understand. So the case in which, for example, the absorption coefficient is constant. So assuming that, under the assumption of a constant source function, assuming that also the absorption coefficient is assumption, it means that also J nu is constant, all constant, all of the three S nu, J nu, alpha nu, let's assume they are all constant. So if you think of the definition, d tau was by definition alpha nu ds, so integrating alpha is constant, so it means alpha s. S in this case is r, is the size of our region. So remembering that by definition of optical depth is just alpha times r. You see that what you have here in the denominator is exactly tau, is exactly the optical depth. So rewriting again this guy here just by replacing the denominator with just tau nu, you can just put among brackets everything which depends explicitly on the optical depth. And again, it's interesting to explore the two different regimes. First regime, optically thin. So when tau is much smaller than 1, so very thin regime. Well, Taylor expanded the exponential and immediately see that the guy among brackets is just approximately 1. Easy to see, okay? So it means that in the case of an optically thin source, I is very simple. It's just the result of the spontaneous emission coefficient times the source, the size of the source, R. And now you should start appreciating the meaning, why the origin of the names. Optically thin, transparent, J nu R. It means that you are somehow putting together the contribution of emission along all the source. J nu is multiplied by the entire size of the source. So, put in another way, you are receiving radiation directly to your receiver, to your eyes, whatever, which is produced in all regions of the source. That's exactly what you say when you say something is transparent. You can receive radiation coming from all the points belonging to the source. You see, that's why it's called transparent. The opposite case, so the other regime, is when it is optically thick. When it is optically thick, again, you see that the term among brackets, the numerator, the negative exponential, of course, is suppressed. So you are just left with 1 over tau nu. So you can asymptotically express the intensity as JR over tau. But again, if you look at this as the product of J nu times, not R, but R divided by tau. So it means that you are not receiving the radiation from all the path R, so all the source size R, but from a tiny portion of it. And what is this portion? R over tau nu. Tau nu is much larger than 1 number. So it means that R over tau is much smaller than R. So your eyes, your receiver, your whatever instrument receive radiation, just receives radiation from a tiny portion, a tiny layer. And the width of this layer is the size of the source, R over tau nu. So the higher, the larger tau nu, and the thinner the portion of the source which you can see, from which you receive radiation. If you move deeper into the source, those points in which radiation is produced, the radiation cannot come to you unaffected, unabsorbed. It goes some reprocessing. In that case, you see opaque. You say opaque. The medium, the source is opaque, indeed, because you cannot see all the inner parts, just a thin layer, the outermost layer, of course. So that should immediately let you appreciate why this quality was called optical depth, and why the two regimes are said to be either optically thin or transparent on one side, and when tau is much larger than 1, optically thick or opaque. Yes, the first point is something that I already said. Yes, I said that the second point is another point. If you want, so okay, in the case of optically thick, I just receive radiation which is produced just in the outermost layer, and the layer we just saw that it's just the width of the layer is just R over tau nu. So you can wonder what's the corresponding optical depth just of this layer, not of the source. We know that the source is just tau nu, much larger than 1. But if I work out the optical depth just of this tiny layer from which I receive radiation, what's the, well, we already said that the width of this layer is r over tau nu. Well, just multiply that to have its own optical depth. Just multiply it by absorption coefficient, alpha nu. So you multiply r over tau nu by alpha nu. So you have in the numerator you have alpha nu r over tau, but alpha nu r is just tau. So the result is just 1. So this optical layer, thin layer from which, when the source is optically thick, this outermost layer from which you receive radiation, the optical depth of this layer is 1. So you can see if you measure the optical depth from outward, moving inward of the source. Of course, when you are on the surface of the source is 0, by definition, you start from here, and then the optical depth starts increasing as long as you move inward. So when the optical depth is measured to be around 1, it means that's the layer which you can see. Beyond the layer, when the optical depth increases much larger than 1, that's the inner layers which you cannot see directly. Okay, we will get back to it, but this is where I advise you at the end of this class to think carefully about that, because when someone first faces these arguments, kind of grasp immediately the general meaning, but all the subtleties, all the details is something that one has to digest and to think with. So I'm aware that I'm putting a lot of things, inevitably, but I'm trying to get as possibly as low as possible. And here, this is another slide which is pretty nice. The first sentence I wrote here is, okay, it is often said that radiation of an optically thick source comes from its surface. And we already know somehow that the flux of a source, by definition, if you think of the flux, depends on the angle between the perpendicular direction to the surface and the observing angle. And there is the famous factor of cos theta. This is another way to look at where the meaning of the cos theta, the origin of cos theta. Well, you know that as a matter of fact, what produces radiation? So just imagine a source which is optically thick. So you see the surface, you get radiation from the surface of this object. And from what we just saw, the radiation you directly receive is just due to an outermost layer, because optically thick. Otherwise, if you could see everything, would be transparent, and the optical depth would be just much less than 1. But radiation, as a matter of fact, is produced by atoms. So atoms live in 3D, not in 2D. So the entity which is responsible for emission is a 3-dimensional entity. So it's a volume. Cannot be a 2D, cannot be a surface. So let's understand exactly in both cases, when you are looking at the source perpendicularly to the surface, and when there is some angle, which I called here on the right panel, theta. Let's work out the volume, which is responsible for the emission. So the volume in which all the atoms which are emitting radiation, you see that straight away. Let's consider this case. Well, I just said that the layer that you see is a layer whose corresponding optical depth is 1. Below 1, you don't see anything. It's not, of course, an abrupt change. There's an exponential, you saw. There's an exponential absorption. But the exponential has a typical length, which expressed in terms of optical depth is 1. So If the layer you see directly, you receive radiation, you receive the photons emitted by the single atoms only if the atoms live in this layer whose optical depth is 1. So something, for example, from A to B here in this drawing. If now, let's assume there's also another observer which is looking at the surface from this direction here, with an angle theta with respect to the normal direction. Now, again, the ray of light just follow this way, follow this path. This path, again, you go as deep as long as the path has an optical depth of 1. But now the ray is this way, has an angle of theta. So the path corresponding to an optical depth of 1 has to be measured in this direction. So if you see that the two lengths AB here and CD here are equal, let's assume that the medium is homogeneous, has the same properties. So in particular, the absorption coefficient doesn't depend on the point within the source. So very simple assumption. We assume that the properties within the source, so in terms of absorption coefficient and emission coefficient, are the same, okay? So since we want both here this path AB and CD have the same optical depth, under the assumption, as I said, of homogeneous medium, it means that they have equal length. But equal length here, it means that dH, so the height of this volume, is cos theta times smaller. Just geometry. If this is 1, okay, this is just cos theta. So the volume which is contributing to the radiation that can reach our observer is cos theta time smaller. So as a matter of fact, if you count, let's suppose you can count the number of atoms which are emitting radiation in every direction. The number of the number of atoms from which you receive directly radiation, in this case, is cos theta times larger than in this case, which explains exactly why the flux between the two cases, there's a factor of cos theta different, because in this case, you see a volume which is cos theta times smaller. So a number of atoms that are radiating towards you, which is cos theta times smaller. So that's why the flux doesn't care about the direction, but at some point. So the flux is just total energy over area per unit time. And if it is specific flux, you notice that here I put among brackets specific. It works both volumetric, both specific. Because here integrating or not along frequency doesn't change the essence, the core of the line of reasoning, okay? So you can apply both things. So that explains why intensity is in this case of a homogeneous source, doesn't change, because intensity is just J tau nu, and JAB, JCD, which are equal. So intensity is the same. What changes is the flux. One can see this, so where cos theta shows up, why there's a cos theta factor. Also in another way, if you look at this thing from the point of view of the observer, you can see that the intensity is the same, but when I move from intensity to flux, or specific flux, you have to integrate or multiply by the solid angle subtended by the source. When you are here, the subtended angle of the source is this guy. When you are here, suppose you are at the same distance, the subtended angle decreases because the projection of the surface gets decreased by a factor of cos theta. So when moving from intensity to flux, in this case, when you are looking with an angle theta, again, the solid angle, intensity is the same, solid angle is decreased by a factor of cos theta, so the flux is decreased by a factor of cos theta. This is another way of looking at it. Again, so two different, but this slide shows you the very volume within the source which you are seeing. You see in one case and you see in the other case. So you see that the volume is decreased because of that. So it's beautiful and it's instructive also to see that from this point of view. So moving on, mean-free path. Mean-free path is something which you heard repeatedly in your studies, but again, it's worth having a look with this kind of formalisms. So we can think of absorption process, just focus on the absorption, just absorption, as a kind of probabilistic process. So a photon is traveling along matter and it has some probability of being observed per unit length, if you think. Okay, let's assume so as I said, just absorption means, in terms of source function, just assuming a null source function, okay? You just have absorption. In that case, if you remember the formal solution of a radiative transfer equation, you don't have the second term, the integral of the source, because the source is zero. So you just have what you have at the beginning of the path, I nu zero, and then this gets suppressed. Well, if the number of photons decreases exponentially, according to the negative exponential of the optical depth, if you think that means that the exponential term is just the probability for a single photon to survive up to tau nu. It's the very same law, for example, of the radioactive decay, the very same. After some time, how many atoms am I left with? Initial number times epsilon times exponential minus the typical lifetime. The very same here. So if you given that here is just one frequency interval, so I is essentially the number of photons times the energy of those photons. So if the number of photons decreases in exponential, it means that this exponential is just the probability for a given photon to survive at least up to tau nu. So let's call it that way. So we call P as a function of tau nu as the probability for a photon of not being absorbed, of survive, of making it up at least up to tau nu. We don't know then whether this will survive even further, even beyond tau nu. So now let's work out the probability that not only does this photon survive up to tau nu, but it is absorbed then between tau nu and tau nu plus d tau nu. So we are making two requirements. We want to survive, so the probability of making it up to tau nu is by definition p tau nu. The probability of surviving up to tau nu plus tau nu is, of course, p tau nu plus tau nu, but we don't want this. So from the probability of making it up to tau nu, we want to remove the probability of making up to a little bit further. So that's why we subtract the probability of course, this is a rare, is little rare making up to a longer distance. So that's why this is clearly smaller. It's more likely to survive up to that point rather than to survive up to a more distant point. So the difference is just the probability of being absorbed exactly in between the two cases. So between S and S plus the S, or tau nu and tau nu plus the tau nu. So that of course, this term is just minus dp. And minus dp is inevitably this guy. So by working out the differential of this guy is just this one. And it's interesting to work out the expected value of tau nu. So you've got many photons. Some of them are going to be absorbed after a small tau nu, after some little bit longer, after the very few lucky ones will be absorbed after a much longer path, okay? So it makes sense to wonder, what's the mean value of tau nu? Here I use the letter E, capital E, and curly brackets. This is a typical notation in statistics, in some cases. Expected. E stands for expected value, which is not exactly the mean value. Anyway, okay, I don't want to, or just put among this this bracket here. So how can I work this out? Well, just multiply. You have to weigh a generic tau nu times the probability for a photon to exactly die at that tau nu, or more precisely between that tau nu and tau nu plus the tau nu, which is exactly what we calculated in the previous case, which is minus dp. So minus dp is the probability for a photon to get absorbed exactly between tau nu and plus the tau nu. So all the photons making this will have a tau nu, which is tau nu. And you have to work out. So by integrating, you are just summing up all the possibilities. And just by replacing this is again very easy integral. I didn't show all the mathematical passages, but just you can integrate by parts. This is very easy. So I think it's just for people like you, for senior people like you, that is straightforward. So this is just one. And if you think of what we saw also before, think carefully, that makes sense. So one is just, remember the layer, the outermost layer in the case of a thick source. This is telling exactly the same thing. So the average optical depth of photon is just 1. So that's why I can consider that essentially most of the photons that I receive come from a layer whose optical depth is 1, for the very same reason. But this is seen from a probabilistic approach, assuming a probabilistic interpretation. Well, if you think we calculated essentially the mean optical, the mean optical depth, but given that between the parallelism, optical depth, and the path, the real path, if you know the mean one, you can also wonder what's the mean path. And the mean path is just what it is usually called as the mean free path. Free between two processes that can affect the photon. So let's work this out. We call L nu as the mean free path. And this, by definition, if you want, of mean free path is just the average path traveled by these photons. These photons get absorbed. So in this case, the process is absorption. So this is just the mean path traveled by all the number of photons that I'm considering. And again, what I will be supposed to do is just multiply Much in the same way as I did here when I calculated the mean value of tau nu, here I did the same. I again use, instead of tau nu, I have to put the quantity I want, whose mean value I want to calculate. So instead of tau nu, S. I here explicitly wrote S as a function of, remember that. And then minus dp. Minus dp is again this guy, negative exponential d tau nu. So this guy here is just again minus dp. Minus dp is the probability for a photon of making it up to of being absorbed between S and S plus ds. Before I said between tau and tau plus d tau, here I changed the variable essentially. So between S and S plus ds, because I'm thinking of S, of the path. But again, we are assuming the easiest case in which the absorption coefficient is constant. So d tau equal alpha ds is tau equal alpha s. So s is tau over alpha, just like that. So here I simply replaced s with tau over alpha. As I said, I'm considering alpha constant, so I can take it out of the integral. And again, the very same integral I was having here before, I know this is 1, so this guy is just 1. 1 over alpha. Look, dimensionally makes sense because alpha is length minus 1, so 1 over length minus 1 is that length. Okay. We also know that alpha can be expressed as a function of the cross-section, so n sigma. So the mean free path equal 1 over n sigma is something that I think you should be already familiar to. You should be already familiar with. So whatever process I'm considering which is affecting something which is traveling, the mean free path is 1 over number density of absorbers, targets, whatever you want to call them, and the cross-section of an individual target. This is a very general formula in physics. But again, this is useful, you see. It's just kind of making linking to something that you already know, but seeing in a different light. But of course, one has to think, no matter how slow I'm trying to explain these things, first time one faces these arguments has to think on his own, on their own, sorry. And so, another way, again, still reasoning in probabilistic terms, but another way to look at this, so I'm insisting on that because it's useful, it's very instructive. It's okay. Our aim is to measure, to describe PS, where PS is wrote here is the probability of traveling unaffected, so unabsorbed for a photon, at least up to S. So the probability of making it up to S, but not up to S plus ds, so the probability of being absorbed between S and S plus ds, well, you can think. You are asking for two independent events. Your first requirement is you want the photon to survive up to S. Second independent requirement, you want the photon to be absorbed between S and S plus ds. So given that you are requiring the combination or logical end of two independent events, the corresponding probability is just the product of the two probabilities. The first one is, by definition of PS, is just the probability for a photon to survive at least up to S. The second one is the probability of being absorbed within the ds path. Why? Well, look, this is the ratio between two areas. The denominator, dA, is the total area. You remember the cylinder I showed many times. The total area, and in the numerator you have a fraction, a portion of that area, which is dA itself, times what? Times the fraction of shadowed area. So what we already commented when we were facing for the first time the absorption. So sigma sigma nu, n ds is the total area shadowed by the individual absorber, times dA is the total shadowed area. So if you get back to how we derived the absorption coefficient, essentially that's the very same line of reasoning, very same. So it's the ratio between the two areas. The shadowed areas by all the absorbers that you've got in this volume, where the volume is just dA times ds. So this is the number, the total number of absorber, and dA ds times sigma nu is the total shadowed area over the total area. So this is indeed the probability for a photon of being absorbed by traveling a length of ds. So you see that the combination, you want the photon to survive up to s, you want it to be absorbed between s and plus ds. So that's exactly this guy here. This means, and you immediately see where the exponential comes from. You see dp over dp. So you integrate this. This is really really easy. And so you recover again what we saw. We recovered it under a different light, in a different fashion, but the result is still the same. So you have a process in which absorption works independently of the individual atoms which are responsible for absorption, and whose capability, overall capability of absorbing, you can describe it in terms of mean free path, or equivalently in terms of the absorption coefficient alpha nu, or equivalently as a function of the combination of n sigma. And the relation between these guys is just what you see here. So remember, the absorption coefficient alpha nu is nothing but 1 over the mean free path. Very simple interpretation, you think. So that should help also. If you remember this, you immediately remember also the dimension of alpha nu, 1 over length. Or if you remember this, it's easier for you to remember that, to recover that. If you remember that alpha is just 1 over length, is 1 over the mean free path. So the longer the mean free path, and the smaller, and that makes sense. The longer the mean free path, it means that the radiation it's easier for the radiation to get unabsorbed. So the absorption coefficient is smaller. So these formulae, I think, is very important, not only because they're relevant in the context of radiative transfer, but also because they're very general. So I wouldn't be surprised if you undergo whatever kind of general examinations, whatever general in physics, if you are testing for your very general knowledge, these kind of relations are very general. So it's worth learning very well, because they can be useful in many different contexts, because they are something very, very general. So, okay, moving on. Let's again insist on exploring all the different ways, all the different meanings. Again, let's consider a source with a size r, constant again absorption, or if you want, now we can say constant mean free path. And let's express with tau the corresponding optical depth, which we know now is alpha r. We knew from the beginning, essentially, but the novelty here is given that alpha is 1 over mean free path, you see tau. Now you have, again, you buy this way, another way of looking at the meaning of tau. Tau is a ratio between what? Between the size of what you are calculating the optical depth for. So having in mind, in this case, a source with the size r. If you want to think of the optical depth of the source, is this ratio between the size of the source and the mean free path. Just like that. So this is also very useful, in my opinion. If you think of optical depth in this term, in many times, in many contexts in which you have to think to deal with the optical depth, this can be very, very useful. So you immediately see the meaning of optically thick and optically thin under a new light. Optically thin is essentially when the mean free path is greater or much greater than the size of the source. So that's why it's transparent, because the probability for a photon being absorbed is very small. Most of the photon will escape. While optically thick, it means that the mean free path is much, much smaller than the size of the source. So that's why most of the photons cannot make it out to the surface, just a thin layer. Let's explore this more in detail. So the two regimes, again, here I'm just showing almost the same things that we've already seen. So again, in the optically thin regime, I is just J nu times the size of the source. So I don't know if you can see. Oh yes, it's much better on the screen here rather than on my computer. So you see, I just wanted to show a source. I could have taken as r the diameter instead of the radius. That's not the point I'm making. I wonder here at the optical depth from the center of the source up to the surface. So in this case, the source is optically thin. I see everything. So I see up to the center at least. And J nu is just J, the intensity is just J, as I said, times the size of the source. And in this case, we know now that the mean free path has to be much larger than R. If you think of the new formula of tau nu as a function of, as a ratio of these two lengths. So that's, if you think of that, that tells you immediately why the source is called transparent. Well, in the other case, again, this is something we already saw, but now, given that tau, you see tau is R over L nu, so R over L mean free path. If you replace here, R over mean free path is just, so this is again a new way of looking at it. So the layer which I can see and whose optical depth is 1 from what we saw is just an optical layer whose optical depth, whose width is comparable with the mean free path, because it's J nu times L nu. So this is what I'm seeing. The dark region is not accessible from an outside observer. So the only layer which is contributing radiation, which can reach, so the photons that are produced within the outer bright layer can make it to the observer, because that layer is just R over tau. But R over tau is exactly the mean free path. Of course, you have to understand this. This is a smooth transition. This is an exponential, okay? But the exponential has, so the wave has a length of the order of. Of course, here the figure has to be clear, so cannot smooth the colors and stuff like that. But this is just the point I want to make. So again, you see, you receive radiation. If you are looking from outside, you can see that's the volume, the The brighter region is the volume from which you can receive directly radiation. And what's the width of this volume? How wide is this? It's just R over tau. So the higher the optical depth, tau here is the optical depth of the entire R, okay? So given that tau is much larger than 1, the larger it is tau, the thinner, so the smaller the amount of. So in this case, optically thick or opaque, you don't see. If you are outside, you don't see below this ray, because photons below that are, almost all of them are absorbed. So this is very important. So, and to test yourself, to test how deep you go with the understanding, how deep your understanding is, you might wonder, so what's the optical depth of this very layer, this outermost layer? Think about it. If it's obvious, the answer, well, that's good. I somehow already said that in between, but just think about it. If you already have the answer, just say, but otherwise think about it. We are seeing the same concepts from many different perspectives. So you should make sure then in the end to see that, but of course it's not straightforward because they're. So the answer is 1. The optical depth of this layer is just 1. Think about it. Okay, so I still have, given that I started a little bit later, not because of my fault, but okay, I will take us, if you don't mind, another 10 minutes, or not longer than 2 minutes. So, this is another very important topic. Thermal and black body radiation, which is shortened in astrophysics as BB. So, well, thermal radiation, what is thermal radiation? Thermal radiation is what you have as a result of the matter which is in thermal equilibrium. But you know very well that matter in thermal equilibrium, for example, think of a gas. With a given temperature, well, you know, if the gas is in thermal equilibrium, you know everything about the gas. You know about, for example, the distribution of velocities of the molecules of the gas, the Maxwell-Boltzmann distribution. You know how the different energy levels are filled up, the Boltzmann distribution, the Boltzmann distribution function. So the exponential of minus E over kT. So you know a lot of things about when matter is in thermal distribution. What about black body radiation? Well, you know that black body is something, for example, black body radiation is something that you can get out of an enclosure which is in thermal equilibrium with a given temperature T. So you make a small hole on the surface of this enclosure. You measure the radiation flux coming out of this small hole, and what you measure is black body radiation by definition. So you measure radiation coming out of the surface, or if you want, coming out of this little hole on the surface of this enclosure. I tell you that the intensity, now we know that we can measure the radiation field in terms of intensity, so we can describe, we can use. I tell you that if I knew intensity coming out of the surface of a black body, this just depends on temperature, nothing else but temperature. And to prove that, let's suppose to make this Gedanken experiment. So let's assume 2 such enclosures, okay, with the very same temperature. We made 2 holes on one body and on the other enclosure, and we make sure that the two holes are facing one another, like in the drawing. So the two holes here are facing one another. Since intensity does depend on frequency, I want to let the radiation pass through only the radiation within a very narrow frequency range. So I use a monochromatic filter. So this object here is nothing but a monochromatic filter. So something which absorbs completely every radiation except for a tiny radiation, except for a tiny frequency interval. So it let pass only the photon, it let pass through only the photons having that frequency, okay? So it's just a way of selecting photons based on their frequency. Now, I say that the two intensities, let's suppose that the two intensities, which I said, the two enclosures do have the same temperature. So, from the second principle, from the thermodynamic second law, or second principle, second law, I say that the two intensities must be equal. Because if they were not, you would have had a net exchange of heat, so a net exchange of energy, which is forbidden by second principle, by the second law of thermodynamics, is forbidden, because if you have two bodies at the very same temperature, they cannot exchange heat. But the only way this cannot be the case is that they must have the same density. So just for the simple fact that you have two black bodies at the very same temperature, if you don't want to violate the second law of thermodynamics, necessarily this implies that the two intensities must be the same. Of course, you can play this game for whatever frequency you like. So the entire spectrum, so the entire intensity as a function of frequency for a given temperature must be universal. All black bodies with a given temperature have to have the same intensity. Otherwise, you would violate the second law of thermodynamics, which is not a good idea. So given that this kind of universal function, I give it a proper name, which I call B. B, as we will see it, is the Planck function, which describes the spectrum of a black body. So the electromagnetic radiation coming out of a black body, expressed as in terms of intensity, so with the units of measure of intensity. Now let's consider a given element of matter with a given temperature. Now, we know that the amount of this element is in thermal equilibrium. Now, the emission properties of this, so the capability of this element of matter of emitting radiation, of affecting a given, let's suppose this is within a generic field of radiation field, the capability of this element to affect the intensity, well, depends on its source function. Think of the radiative transfer equation. You put some matter, well, depending on the source function of that matter, intensity is affected as a consequence. So let's call S nu the source function of this element of matter with temperature T. I tell you that this guy, the source function of this guy, is exactly the Planck function. Why? Well, let's suppose you put this guy in front of the whole of the enclosure, which is a black body, which you already considered before. If you put this piece of matter with temperature T, so the very same temperature as the enclosure, you put facing the whole of the, again, you are putting very close two bodies which have the same temperature. So you are not expecting to see exchange of heat. But if you think in terms of the radiative transfer equation, it means that the intensity field coming out of the hole cannot change because you put this element. You put all of things, we have the same temperature. So from the thermodynamic point of view, nothing has to change. So in particular, the radiation field cannot change. In particular, I cannot change. So I cannot change, it means that the derivative of I along whatever path you consider is 0. But that means that I equals S, radiative transfer. But I is B because I'm just in front of a black body. So it means that whenever I have some matter in thermal equilibrium with a given temperature T, the source function of that matter is necessarily the Planck function. But remember, the source function by definition is emission over absorption coefficient. So what we just proved is the so-called Kirchhoff law, which connects the emission properties and the absorption properties of matter. Which matter? The matter which is in thermal equilibrium. So matter which has a given temperature T. So whenever you have something in thermal equilibrium, some matter, some gas, whatever, which is in thermal equilibrium, has its own T, its own temperature, the emission and the absorption capabilities are strongly connected, and in particular their connection is ruled by the Planck function. So J nu is nothing but alpha nu B Planck function. This is called Kirchhoff's law, as I said. And you see, the source function is something different from I. Now you can take this element of matter, temperature T, and put in a context in which the environment temperature is not necessarily the same temperature as the element of matter. In that case, the source function is still the same. The source function is something which characterizes the emission and absorption properties of the matter. But if the matter is in thermal equilibrium, has temperature T, well, that's the source function. What will change eventually, possibly, is the I. So I can change depending also on the environment. But the source function of matter, which is in thermal equilibrium, just depend on the property of matter, not on the field, on the environment in which matter is. We will see in the next slide, not today, because I already put many things. We didn't go through too many slides, but they are very dense, conceptually dense slides. So I don't mind stopping here because I think you'd better benefit from thinking in the next 5 days or so about all these concepts. And we will explore from next time the difference between thermal radiation and black body radiation. You will appreciate the difference between the two cases, which are not necessarily equal, they're different. In general, they are different. Speaking of thermal radiation is something, speaking of black body radiation is something else. And this is very important. And understanding this difference is strongly connected to understanding the difference between I, the brightness, and the source function. We will see, I can just foretell you that we will see that thermal radiation is when the source function is black body spectrum, so is the Planck function. But nothing can be inferred about I. You've got black body radiation when not only the source function is Planck, but also when I is the Planck function. In that case, it means that the equilibrium is not just thermal equilibrium of the matter, but the matter is also in equilibrium with radiation. So in this case, it is said thermodynamic equilibrium, to mean that there is equilibrium between radiation and matter. So black body radiation is something stronger. You can have thermal radiation and not have black body radiation. We will go through it. This is kind of subtle thing, but because sometimes even professional researchers can occasionally make some confusion. They can talk of thermal radiation and they think of black body radiation. They're not the same. I can already foretell you that given that this topic is, as you see, is going to take us several classes, one of the main references, this is one of the most important textbooks in this field in astrophysics, sure, is the Rybicki-Leitman. This is the first book which is reporting the references in the last slide. So I'm following more or less adherently that textbook, and then also these are linear. This is my main reference because this is very rigorous. It's a combination, but anyway. Okay, so sorry, I apologize for the slight delay, but again, I keep apologizing for the delay, which I inherit from the previous lecture, so it's not entirely my fault. So any questions? Okay, so just think about what I said. I said many things.